In section 8.1, we're going to describe the formation of covalent bonds in terms of atomic overlap, and we're going to define and give examples of sigma and pi bonds. So, Linus Pauling and others developed the valence bond theory of covalent bonding. Linus Pauling won his Nobel Prize for his theories on crystallography and bonding. He wrote the book, The Nature of the Chemical Bond, which for a long time was the book on the subject. He said that electrons reside in orbitals. Covalent bonds form when electrons are shared by the overlapping of singly occupied orbitals. Electrons in these overlapping orbitals must have opposite spins. So if you think about the formation of a bond in H2, if this is the distance between the two nuclei, at some optimal point, the energy will be at its lowest, and this will be the bond distance that it wants to have. If you push them any closer and lower that bond distance, the two nuclei are going to repel each other, and the energy is going to spike up really high. If you start to pull them any further away from each other, then you're going to be inputting energy to break that bond, and the energy is going to go higher and higher until you reach the bond breaking point. The distance between this center line of zero energy and this optimal point right here is going to be the dissociation energy for that bond. To form a covalent bond, an atom must have an unpaired electron. The number of bonds formed by an atom is determined by the number of unpaired electrons. This theory works well for explaining the bonding in diatomic molecules with only single bonds. This theory also works well for explaining the lack of bonding experienced by noble gases. Here we can see the overlap of two p orbitals in a direct end-to-end connection. And if you tip them in any one way, if you orient them in any other way, you're going to see less orbital overlap. So this is going to be our preferred configuration. And when bonding happens like that, we call it a sigma bond. This is a covalent bond in which the electron density is concentrated in the region along the internuclear axis. All sigma bonds all single bonds are sigma bonds. So that starts off by forming these sigma bonds. After that, double bonds and triple bonds are what they call pi bonds. This is a type of covalent bond that results from the side-by-side overlap of two p orbitals. So multiple bonds are mixtures of sigma and pi bonds. Here we can picture some sigma bonds from two s orbitals. Here's an s orbital with a p orbital, and here is it with two p orbitals. Pi bonds occur when we have the other two p orbitals, because remember those are at 90 degrees from each other, and they have a side-by-side interaction. So you're going to have this one, and then if you imagine this turned 90 degrees along the internuclear axis, there could be another interaction leading to a triple bond. So remember, we always begin with sigma bonds. So in a single bonded system like this, we have one sigma bond and no pi bonds. When we do a double bond, we have one sigma bond and one pi bond. And then a triple bond is a sigma bond with two pi bonds. In section 8.2, we're going to explain the concept of atomic orbital hybridization. And we're going to determine the hybrid orbitals associated with various molecular geometries. So valence bond theory works well for linear and diatomic molecules, but it fails to account for the molecular structures we know more complex molecules have. We saw how VSEPR theory was able to recreate the molecular geometries pretty well. But how can we rectify molecular geometry with the bonding based on atomic overlap? So if we look at valence bond theory in the case of water, we get the wrong geometry. We see that these are about 90 degrees apart, and we know that to actually be closer to something like 104. So we introduce hybrid orbitals. And this is where we're going to combine together orbitals of different kinds, S and P's and stuff, to make a hybrid orbital, which is essentially like the mathematical addition of those two areas that the orbitals would occupy. One thing to keep in mind when working with hybrid orbitals is that the number of hybrid orbitals formed always equals the number of atomic orbitals that are combined. So here we can see that VSEPR theory would predict that in a water molecule we have a distance of 109.5 degrees to form a tetrahedron. We justified that it was less than that before by saying that the lone pairs are going to occupy more space. But we'll see that with atomic or hybrid orbitals, we actually don't even need that justification. We actually get down to 104.5 degrees, a lot closer with our experimental results. So what are hybrid orbitals? We're going to combine together orbitals of two different kinds. We'll start with just a single S and a single P. The two atomic orbitals can hybridize to produce two hybrid orbitals. These are called two sp hybrid orbitals. This occurs when a central atom is surrounded by two regions of electron density. Unoccupied orbitals cannot hybridize. So let's take a look at what that looks like. So if we have an s orbital and we have a p orbital, their mathematical addition is going to look something like this. We're going to have two hybrid orbitals for the two orbitals that we put in. And when we combine those two together, we wind up getting an orbital that looks like this, 180 degrees apart. If we think about the electronics of that situation, we had two electrons in our s orbitals. In the case of beryllium, after hybridization, one of these electrons is promoted to a p orbital, and we wind up with two sp orbitals and two unhybridized p orbitals at the top. We can have sp2 hybridized orbitals. This is when three atomic orbitals can hybridize to produce three hybrid orbitals of the sp2 type. This occurs when the central atom is surrounded by three regions of electron density. So this time we're going to have two p orbitals. We're going to start with the one that would be end-to-end with the s orbital, and we'll add in one of the other ones. It wouldn't really matter which one. And we're going to wind up with three orbitals that look like this, each aligned down one of the axes. When we combine those together, we wind up with a planar structure with 120 degrees apart. We could also visualize that by essentially looking down this z-axis, and you'll see that drawn commonly when you have crowded structures. Picturing the electronics of this situation, we have three electrons this time, one of them in a p orbital. We wind up with three sp2 orbitals, each singly occupied. Here are some examples of some sp2 hybridized orbitals, or hybridized structures. You're going to see this written a lot in organic chemistry. They'll be talking a bit about the hybridized orbitals. And of note here is on ethylene. The hybridization is actually occurring on both of these carbons. So this guy here is sp2 hybridized, and so is this one here. if you imagine that there is a 1 above the S, then 1 plus 2 is 3. And that will always be the number of things that carbon binds to in when you're trying to figure out the hybridization for carbon. So if it was bound to 4 things, it would be sp3 hybridized. If it was bound to 2 things, it would be sp2 hybridized, or I mean sp hybridized, and so on and so forth. sp3 hybridized orbitals is when we have 4. We're using all 3 of our p orbitals now. We get 4 hybrid orbitals, and those are going to combine into that tetrahedral type shape. This time we are using all of our p orbitals, and we wind up with no unhybridized orbitals left over. Here we can picture the formation of ethane here. So we have 1 carbon bound to another carbon, and then 3 hydrogens bound to the periphery of those. We can actually extend this even further when we have metals by including d orbitals. So we can have sp3d hybridization, and that is going to yield us to our trigonal bipyramidal structure. And we can even have sp3d2 orbitals with 6 atomic orbitals, hybridizing to give us our octahedral structures that we've seen with metals before. If we compare the structures that we got from VSEPR theory with our hybridization model, we see good agreement, and we can now describe 3-dimensional geometries. In section 8.3, we're going to extend our idea of hybrid orbitals to allow for multiple bonding, and then we're going to extend that concept to the idea of resonance that we learned about before. A little refresher here: single bonds are formed by sigma bonds, and multiple bonds are formed by pi bonds. Pi bonds are not created by hybrid orbitals. Hybrid orbitals only form sigma bonds. Multiple bonding occurs from the unhybridized orbitals that are left over. To determine the hybridization in molecules with multi-bonds, recall that a double or triple bond is each one region of electron density. So if we look at our molecular orbital diagram, prior to this, we had just enough electrons to fill all of our hybrid orbitals. But what happens when there's enough electrons for an electron to go into one of these unhybridized orbitals? If we look at the case of ethylene, we can see that there are these p orbitals that are still present here, unhybridized. If an electron goes in there, then they're going to form this side-to-side interaction, producing a double bond. If we think of the case of benzene, each one of these carbons is just as happy to form that side-to-side interaction with either one of the carbons next to it. It would just as much prefer to be here as it would prefer to be here, and in fact, it's going to go back and forth, forming those side-to-side interactions with its neighbor really fast, back and forth, to make a resonance hybrid. Triple bonds can be formed when there are 2 unhybridized orbitals, each with an electron in it. In this case, we're forming acetylene through 2 side-to-side interactions with those p orbitals. Section 8.4, we're going to outline the basic quantum mechanical approach to deriving molecular orbitals from atomic orbitals. We'll describe traits of bonding and anti-bonding molecular orbitals. We're going to calculate bond orders. We're going to write some molecular electron configurations for first and second row diatomic molecules. We'll relate these electron configurations to the molecule stabilities and magnetic properties. So first, the magnetic properties. Molecules that have unpaired electrons are attracted to strong magnetic fields. This is known as paramagnetism. Molecules that have all paired electrons weakly repel magnetic fields. This is known as diamagnetism. This phenomenon can be measured by a magnetic susceptibility balance. This technique measures the precise mass of a sample in the presence of magnetic fields of varying strengths. So if we picture that I put a sample inside of a container and I can accurately weigh its mass, obviously we wouldn't use one of these, we'd have like a electronic balance. And I put it in between two magnets, electromagnets, where I can control this magnetic field and vary it. I can measure the magnetic susceptibility of that compound by seeing how the mass changes as I vary the magnetic field. Molecular orbital theory. So far we have been talking about overlapping atomic orbitals forming bonds. In molecular orbital theory, those atomic orbitals actually combine together to form a new orbital that encompasses a larger part of the molecule. Molecular orbital theory describes bonding and electron density as molecular orbitals. The molecular orbitals are similar to atomic orbitals except they span an entire molecule. The behavior of the electrons is described by the wave function that we talked about before, and it's limited to discrete quantized energy levels. The probability of an electron being found in a region around a molecule is described by the product of the complex conjugates of the wave function, which we're going to write as psi squared. Psi squared determines the shape of the molecular orbitals. You always wind up with the same number of molecular orbitals as you had atomic orbitals to begin with. So atomic orbitals are combined to form an equal number of molecular orbitals. The mathematical process of combining the atomic orbitals is called linear combination of atomic orbitals, LCAO. And LCAO is a special case of the law of superposition, which you may learn about in differential equations. Combining these wave functions can lead to constructive interference, resulting in regions of higher electron density, and it can also lead to destructive interference, resulting in regions of lower electron density, exactly as we saw for electromagnetic waves. In-phase and out-of-phase combinations. So our in-phase combinations produce lower energy sigma s molecular orbitals. The out-of-phase additions produce a higher energy sigma star s molecular orbital. Sigma s focus orbitals focus electron density between nuclei, holding them together. We call these bonding orbitals. Sigma star s focus electron density away from the bonding region, pulling the nuclei apart. So we call these antibonding orbitals. So if we take the case of two s orbitals and we consider their atomic overlap, the possible molecular orbitals they'll make could be antibonding, bringing the two nuclei apart, or bonding, overlapping, and bringing the nuclei together. We can picture this for p orbitals as well, forming an overlap along the internuclear axis or an antibonding orbital along the internuclear axis, and we can extend this to side-to-side interactions like we've seen before. So Relative energy levels of atomic and molecular orbitals are typically shown in what we call a molecular orbital diagram. Atomic orbitals of one atom are shown on the left, and those of the other atom are shown on the right. Each horizontal line represents one orbital that can hold 2 electrons. Molecular orbitals formed by the combination of atomic orbitals are shown in the center. We use dashed lines to show which of the atomic orbitals combine to form the molecular orbitals. For each pair of atomic orbitals that combine, one lower energy bonding molecular orbital and one higher energy antibonding molecular orbital result. Electrons are filled into these molecular orbitals using the Aufbau principle. So we're going to fill lower energy orbitals first, where electrons are going to spread out among degenerate orbitals. So those are orbitals that have the same energy before we pair them off. And each orbital is going to hold a maximum of 2 electrons with opposite spins. Here we can see our Aufbau principle. If we had 2 electrons in a 2s orbital and 1 electron in a 1s orbital, we're first going to put 1 electron in this bottom energy level. We'll next pair it off. Then we'll move up to the higher energy level and put another electron. If we look at the example of H2, we can see that we have 2 electrons in our lower energy bonding sigma 1s orbital. That's going to predict that H2 will be a stable molecule with a bond order of 1. Helium, diatomic helium, on the other hand, has 2 electrons in an antibonding orbital and 2 electrons in a bonding orbital down here. These are going to cancel each other out, so we wouldn't predict that diatomic helium would be stable, and it is in fact not. Bond orders. So an electron contributes to a bonding interaction if it occupies a bonding orbital, and it contributes to an antibonding interaction if it occupies an antibonding orbital. The bond order is calculated by subtracting the destabilizing antibonding electrons from the stabilizing bonding electrons. Since a bond consists of 2 electrons, we divide by 2 to get the bond order. So bond order is the number of bonding electrons minus the number of antibonding electrons divided by 2. You'll see that this actually does allow for there to be fractional bond orders, such as 1.5 or 2.5 or something like that. In molecular orbital theory, sigma orbitals are usually more stable than pi orbitals, but not always. Atoms with 3 or fewer electrons in the p orbitals, so lithium through nitrogen, we observe a different pattern in which the sigma p orbital is higher in energy than the pi p set. This switch in orbital ordering occurs because of a phenomenon called sp mixing. And xp mixing occurs when the s and p orbitals have similar energies. So it's not really important to understand s and p mixing, but just to know that this sigma 2px orbital is going to be higher in energy than the pi 2py and 2pz orbitals in cases where we have lithium, beryllium, boron, carbon, and nitrogen. And then from oxygen on up, we're going to see the pattern that we would expect it to have in all those cases. So that means that in the case, a more complicated case here, where we're trying to make diatomic atoms, we're going to need to move this sigma p up above these 2 pi orbital molecular orbitals here. So let's look at the case of oxygen. Oxygen has a 2s atomic orbital. These two are going to combine to form these sigma 2s and antibonding sigma star 2s orbitals. These two will cancel each other out. Therefore, the 2s electrons really aren't participating in bonding in the case of oxygen. If we go up to our 2p atomic orbitals, when they combine, they form 3 bonding orbitals, the sigma 2px and the pi 2py and the pi 2pz. We're going to fill all of these up, giving us a bond order of 3. But then we still have 2 electrons that we have to put into these antibonding orbitals using the Aufbau principle. We'll put 1 in each one, and that's going to reduce our bond order down to 2, giving us the double bond that we would expect oxygen to have. Band theory. So, in a solid, a huge number of atomic orbitals may be combined into molecular orbitals. When n valence atomic orbitals, all of the same energy and each containing 1 electron are combined, n divided by 2 filled bonding orbitals and n divided by 2 empty antibonding orbitals will result. The allowed energy levels for all of the bonding orbitals are so close together that they form a band called the valence band. Likewise, all the antibonding orbitals are very close together and form a band called the conduction band. In order to conduct electricity, electrons must move from the filled valence band to the empty conduction band. The size of the band gap determines how easy it is to move electrons between the bands. In conductors, the band gap is very small. In an insulator, the band gap is large. Semiconductors have moderate band gaps and conduct electricity only under certain conditions. So we can see now that using molecular orbital theory, we have a theory behind conduction that allows us to determine whether or not something's going to be an insulator, semiconductor, or conductor, if we can get a sense of how large this band gap between this valence band and this conduction band is. It is kind of interesting to note that this is temperature dependent. So semiconductors, under really cold conditions, we can actually decrease this band gap down so that we get good conduction between them.